Usually, yeah. If it's a chain rule thing, as you get more layers, typically they look
You
bigger.
shouldn't worry about getting it small.
Well, no, I mean, you want to simplify it, but you don't want to, there's not a ton you can do. Like with this one, we'll see, there's not a ton you can really do with it. Okay, so what's the first layer?
This would be cosine tan.
Okay, good. So cosine hand. Derivative of sine hand is positive cosine of hand, right? And how about if I liked what I did yesterday. That was kind of a cool deal. So if we'll just erase the layers one at a time over here, how about? So there's the first layer we've taken care of. Okay, next layer. Oh, I guess I should write those in there. So what is inside? Now that we look, it's a square root of x squared plus 1. Okay, we didn't specifically rewrite this, but how would we deal with this next layer? 1/2 power. Okay, so what's the derivative of hand to the 1/2?
1/2 hand to the -1.
Very good. Okay, and hand is an x squared plus 1. We can erase the radical. That was our next layer. And then finally,
2x.
2x. Okay, so what would we do here to simplify this then?
2 and 1/2 cancel, put the x out front.
The x would go out front, good. So then we're going to end up with y prime equals x is out front. Cosine of junk, and then
Over the
radical of this.
good.
square root of x squared.
Good. Okay. Very good. Okay, so the next issue. So what I want to look at now, now that we've amplified our number of derivatives we can handle with chain rule, what happens if we get a quotient or a product that involves chain rule also? Okay, so for example, let's look at two of these. Let's look at one. How about something like this? What if we say y equals the quantity x squared minus 1 times square root of 2x plus 3. So now we have to look at this, and let's actually, hang on, let's make that a 2x squared, and let's make that a cube. Okay, so at the outermost layer, what kind of a pattern do we have here? So when we want to do what you're going to find is, I know this, you're probably going to throw stuff at me for saying this now, but later on you'll feel the same way. Later on this year you'll feel the same way. Differentiation is just easy because their rules are easy to follow. Once you learn I know it's hard right now because you're just starting it, but once you start to learn the rules and become familiar with it, it's not very hard. I mean, there's other things that we'll do that you have to think about a little more than this. And this is just a matter of picking out the rules. What's the rule there? At the outermost level, what's the rule that applies? Well, okay, there is chain rule in there, but there's something else going on. It's a product. Yeah, when I look at this, I see, a factor times a factor, right? There are two things that are being multiplied, and so the pattern that's going to guide the differentiation here is we got to follow the product rule. Now, within the product rule, yeah, there's going to be some derivatives that are going to be multiple layers that are chain rule derivatives, right? But you see what I'm getting at here? When you kind of try to establish from the outside in, what is this thing? Well, it's a product. I've got something times something, right? Everybody see that? Okay. Okay, so what do we do then? If we're going to differentiate this, we got to follow the product rule. So what is that? Okay, so we can take the first thing, which is x squared minus 1 cubed times the derivative of the second. Now that's a chain rule issue, right? But that's all right. We're just, we in calculus a lot of times you got to kind of think at a big level, what's the pattern, and then once we dive into the lower level stuff, still might be, we got to do the task of taking that derivative. That's a part of the big process, right? So what is the derivative of this guy? Okay, I got a 1/2. At the outermost level, it's hand to the 1/2, right? So I got a 1/2 hand to the negative 1/2, good, okay. And then inside we get a what? Okay, good. So if we were to label those parts, then this is the first part. Like if we call this one U and this one V, isn't this just U times V prime? Okay, so then the next part would be plus V times U prime, right? So what's that going to be? Good, so okay, so we get second part, so 2x squared plus 3 times, what about this one? Okay, good, the outermost layer is going to be a cube, right? So we've got hand cubed. Derivative of hand cubed is 3 hand squared, right? And then inside 2x. Okay, everybody agree? Okay, so now let's do a little cleanup here, because what this is about mostly, the calculus is done, right? The calculus was not that big a deal. And I've told you this before, and now you're seeing it's true, that a lot of this class is algebra. You're going to do more algebra in here than you've ever done by far. It's, like from here on out, the hard part of this problem is just collecting it together and making it look right, factoring it and simplifying it. So let's do a couple things. Let's take, how many terms do we have up here? No. No. What are terms? Factors are things that are multiplied, right? What are terms? The answer is 2, yeah. Terms are things that are added or subtracted, right? So we've got 2 big things that are being added here, right? I've got this big term and then this big term. Everybody see that? Okay, that's the structure of this answer. We've got 2 big terms here. So I'm going to put a circle around that so we can track that plus sign that's separating the 2 big terms. Let's focus on the first term. What can we do in the first term to make things easier? Okay, we can't distribute exponents because remember, x squared minus 1 cubed, if I do this, if I do a plus b or a minus b cubed, that is not equal to a cubed plus b cubed, right? Does that make sense? It's a plus b times a plus b. It's much more complicated. And we don't want to do that anyway. And that's a reasonable thing to suggest. But looking ahead here, ultimately what we're going to want to do with this, if we think ahead to what we're going to do with derivatives, we want to have them factored. Because we've seen a couple, just a smattering of these little problems where they've asked you to do things like find all the places where the function has horizontal tangents, right? That's a big deal for us. Later on in the class, very soon, that's what we're really looking for, are places where we have horizontal tangents, or we want to look for peaks and valleys. And calculus is what helps us do that. We also will eventually look for things like inflection points, which is, looking at higher level derivatives, their manifestation in a graph. But we want things factored because we want to be able to find zeros of our derivative. And if you think back to algebra and pre-calculus, I mean, what did we always try to do? When we're trying to solve a complicated equation, we want to factor it, right? So we can set the factors equal to 0 by the zero product property. So we like factors. We don't want to undo the factors that we've got there. All right, so we got these 2 big factors. Is there some simple stuff up here? I mean, like for example, we could say that 1/2 times 4 is 2, right? Everybody see that? Let's go ahead and then what do we have on this side? Well, we've got, really we can't do much. We've got an x times an x squared minus 1 cubed times a 2x, you're right, sorry, 2x times an x squared minus 1 cubed times the quantity 2x squared plus 3 to the minus 1/2 plus, how about over here? Well, there's not a lot we can do there. We can just combine the 3 and the 2, which is going to give us a 6x. And then we've got an x squared minus 1 squared times, if I want to write this as a power, wouldn't that just be a 2x squared plus 3 to the 1/2? Everybody agree?
So I, for the first part, can you, put 2x times x squared minus 1 to the third over this square?
You could, and that's an okay thing to do, but I didn't for a reason here, and you'll see why in just a second. You could. Okay, so now what? This looks like a mess. I've got 2 terms. What do we typically try to do when we have multiple terms? Well, we combine like terms if we could, but man, these are not like terms, are they? Right? What else do we try to do? Remember, our goal is we want to put this in factored form. Factor out, okay, well, we're going to factor out greatest common factors. For example, I've got an x is a common factor, right? And a 2 is a common factor, right? So let's factor out or undistribute as much as we can that's in common to both terms, right? Now look at, you see something interesting going on here. Do you see that the bases are the same bases, aren't they? Right? Like we'll make this our yellow base, x squared minus 1. Well, look right there. There's an x squared minus 1 base. When I say base, you know what I mean, right? A power consists of a base and an exponent. So this is a power and this is a power, and they have like bases. Okay? How about this? 2x squared plus 3. There's a like base. Is that an accident? No, it's not. If you look back at what we did with the product rule, we've got these 2 powers here, don't we? This is a fractional power, but I've got 2 powers. Each of these powers has its own base. Well, when I do the product rule, in each term of the product rule, I'm going to have a base times a base to a different power. I'm going to subtract 1 from each exponent, right, in the first and the second terms. But the bases stay the same, right? When I do the power rule, think what the power rule does, the generalized power rule. If I'm taking the derivative with respect to x of u to the n, and this is going to be the way we're going to write this from now on. We're not just going to limit ourselves to having x to the n. Now we can do a function of x, right, with the chain rule. What do we get back? Well, the derivative of hand to the n is n times u to the n minus 1. And then if we look inside, what's the derivative of u with respect to x? Well, we'll just call that u prime, right? So we don't have to just we no longer are limited to just saying the derivative of x to the 7th. We could say the quantity 2x squared minus 3 to the 7th, if that's what u is for us, right? Okay, and we'll go back and talk more about this notation here in a second. That's not important at the moment. The only point I wanted to make is that, well, look, that's a power with a base u, that's a power with a base u, right? The base stays the same, but the exponent changes, right? So it's not surprising to us that we're going to get pairs of like bases when we do the product rule or the quotient rule, okay? So now this helps us out a lot, and we've even got this other one thrown in there. We even get an x that's a common factor also, right? So what are the things that we can factor out of this then? So we can take out a 2x, right? What else could we take out? Okay, there's a like.
Minus 1 squared.
Okay, we could take out an x squared minus 1 squared because we're taking out the least common or the greatest common factor, right? Which is, now what does that mean? The greatest common factor means it's going to be the smallest common exponent, right? It's going to be the smaller of the 2 exponents because, in a manner of speaking, x squared minus 1 squared is included in x squared minus 1 cubed, right? But x squared minus 1 cubed is not included in x squared minus 1 squared, right? Everybody see that? So we'll factor out the greatest common factor, which is going to be the smallest power of each base. So we get an x squared minus 1 squared we can take out. And then how about these? To which power? To the negative 1/2, right? Good, so we'll take out a 2x squared plus 3 to the negative 1/2. And what's left behind if we do all that stuff? Well, from the first term, the 2 and the x are gone. This is completely factored out, right? Now, what's left over from this power? If I'm dividing away, if I'm undistributing an x squared minus 1 squared from an x squared minus 1 cubed,
X squared minus 1.
it's x squared minus 1, isn't it? Right? Is it an accident that it's to the first power? No, because in the product rule, we subtracted 1 from that base, and that's why they're different by 1, right? Why the exponents differ by 1, because of what the power rule is. When we take the derivative of x squared minus 1 cubed, for example, we're going to end up with x squared minus 1 squared. We're subtracting 1 on purpose from the exponent, and we do the same thing for the other base, right? So they're always going to differ in power by 1, by the integer 1. Okay, how about, so we end up then with, from the first term, we end up with x squared minus 1. Plus, what do we end up with from the other?
3x.
Okay, so we get a 3, good. We get a 3 from this guy. And so that becomes, where's this? So that becomes a 3. That goes away because we factored out the x, right? This is completely factored out. And we're left with what power of 2x squared plus 3?
Negative 1.
You sure?
It'd be negative 2x squared minus 3.
So when we, let's think about this now. If I'm going to undistribute or divide away, because that's really what I'm doing. When I factor something out of a term, what I'm left with is that term divided by the common factor, right? So let me ask you this. What is 2x squared plus 3 to the 1/2 divided by 2x squared plus 3 to the negative 1/2? Because that's what I've divided away from this.
2x plus 3.
2x to the 1. Once again, you know it's going to be to the 1, don't you? Right? Because they differ, the exponents differ by 1. So we're left here with 3 times the quantity 2x squared plus 3. Right? Well, that looks pretty good. We can take now this, so we've got how many factors here total then in our answer? 1, 2, 3, 4, right? That fourth one's a mess, but we can clean it up pretty easily, right? You see that? We factored out 1, 2, 3 common factors from each term, right? From each of the 2 terms. And then we had a leftover part from the first term and a leftover part from the second term after factoring, which we can combine into the other factor, right? The leftover factor. Okay? Right? Make sense? So let's do the algebra then on this last part. So first part's done. So what are we left with here then?
7x.
Okay, good. So we get 7x squared plus x squared, 7x squared, and then 9 minus 1, so plus 8, is that right?
Yep.
Yeah.
There's my derivative. And so if we want to write this now as a ratio, I guess maybe the last step would be, what goes on top? Well, all that stuff, right? Well, no, that and that and that. divided by, how can I write this?
Square root of 2x squared.
There you go. Okay. Okay, that looks like a mess probably, but that's really useful because now if we wanted to analyze this derivative function, where would the derivative function be equal to 0? I mean, don't tell me exact answers, but how would I know? Say it again. Now, where's the fraction equal 0? When the top or the bottom equals 0? When top is 0. So I could set the numerator equal to 0, and it's already factored for me, right? So the zeros of the derivative are going to be the zeros of 2x, x squared minus 1, and 7x squared plus 8, right? Which individually aren't hard to find. Where is the derivative going to be undefined? Any place where the 0, or excuse me, where the bottom is equal to 0, which is, where's the bottom 0?
Square root of 3 over 2.
Okay, so are there any x values? Can you tell me what x values make the bottom 0?
None.
Okay, but I'm squaring the x, right? So none is right. Does that make sense? This, I mean, this is just a kind of a side question, but it's a good question. And later on, we'll deal with stuff like this a lot more. How would you analyze the bottom here? Well, we're just asking the question, we have a square root. If I'm really trying to find all the zeros of the denominator, we've got a square root. So everything in the square root has to be non-negative, right? Everything in the square root has to be greater than or equal to 0. Well, what's in the square root? 2x squared plus 3. So if I solve that, I could add 3 to this side and divide by 2. I'd get x squared is greater than or equal to negative 3 halves. Well, that's always true because x squared is non-negative, right? See what I'm saying? And we probably could have just looked at this, you know, if we from the beginning and said, okay, well, that term right there, 2x squared, is non-negative, meaning it can't be negative. If I add 3 to that, it's positive. The argument of this square root is always positive, so we're fine. We're in the clear, right? There are no values on the bottom that would ever make it undefined, make the bottom 0, right? I mean, that's just a little side note. That's not a big deal. This is the goal. Our goal was just to get this function, which we did. Okay, why was I so eager to show you an example like this? Well, because of this, whenever you do a product rule or a quotient rule derivative like this, it's a big one that involves chain rule stuff, right? You're going to end up with, it looks terrible, but there's a lot of structure to this, right? We get these common factors, these like bases that we can factor out. You see that? Let's do one quotient rule one. And then, I think then you just got to work on stuff. So I'll let you guys have tomorrow as a work day. I'll just make one up here. How about, let's do this. I'll make this hard. Let's do this. This will be good. Okay, so first of all, is there a way that we could write this so it's not a quotient rule problem? Okay, good. So what would I do? So I could, if I wanted to, I could write this as the quantity 2x cubed minus 3x to the 5 halves times x squared minus 3 to the negative 4, right? Okay? Okay, take your pick. I mean, either way is fine. It doesn't matter. Let's do this, being as we just did, excuse me, we just did a product rule. Let's do this as a quotient rule problem. Okay, but you could, if you prefer, you can just do it this way. Okay? All right, so if we do this as a quotient rule problem, because there's a thing you can do here that I want to show you. It's kind of cool. What's that going to look like? What is it? Low, low D high minus high D low, right? Okay, so we got bottom times, yikes, derivative of the top. What's that? Three halves, good.
Times 6x squared minus 3.
Times derivative of what's inside, which is 6x squared minus 3. Okay, good. Minus minus what? Oh. Look, hey, she's not here. Lily's not here. Look back to you. Okay, so what's the next part? Okay, I'm gonna go ahead and write it. I'm gonna write the top first, and then you can do it the other way if you wanted, but I just am in the habit of always doing it this way. I put the non-derivatives first and then the derivatives. Times the derivative of the bottom, which is derivative of hand to the fourth is 4 and cube times, oops,
Times 2.
okay, what's the other part then? Okay, it's over b squared, right? So what is x squared minus 3 to the fourth squared? To the eighth. There we go, okay, yikes. Yikes. Okay, so what can we do here? So there's the calculus. Now it's a matter of just factoring stuff out, right? Well, what about the denominator? The denominator is a common factor in a sense, isn't it? It is a common denominator. So we could pull that out with our factors, okay? So then we end up with the greatest common factor. We've got an x squared minus 3 to the eighth. And now let's separate these into two terms. Okay, what can we take out from the first term? We can do this quite a bit.
2x cubed minus 3.
Okay, let's see if we can take out some. Say it again.
Couldn't you take out x squared minus 3?
We're going to be able to take out some x squared minus 3s. You're right, and we will be able to do some cancellation. Yeah. So on the top, let's start with numbers. Is there a number? Now here's what I do. This is, and there's a reason I do this. I would prefer to get rid of that 5 halves because it's a fraction, right? So I'm going to undistribute a 5 halves from both sides. Okay. Say it again. Where do you see in the? Oh, I could take a 3 out there, couldn't I? No, you can't do that because 2 1/2 is 2 plus 1/2, right? So, so then we could rewrite this though. Let's do one little thing here. Let's factor out of this guy. Let's make that equal to 3 times x squared minus 1, right? We could do that. Okay.
Would that be 2x squared minus 1?
Oh, you're right. 2x squared minus 1. You're right. Okay, so what can we do here? What do we have common to both sides then? Well, let's just like maybe underline the bases that are common. So we've got an x squared minus 3 there and there, right? And we've got a 2x cubed minus 3x there and there. And that's it, right? Everybody see that? There isn't even technically a common integer that I can factor out. But just for the sake of convenience, I'm going to force an, I'm going to, how do I say this? I'm going to like to force the factoring out of a 5 halves, which means I'm just going to divide each side through by 5 halves, right, to see what's left over. Because I want to get rid of that fraction. I don't want to deal with the fraction having to distribute. It's not a huge deal. I mean, you guys can do fractions, but I don't want to deal with all the math in here when we're doing all this simplifying of having to cope with that 5 halves the whole way. I'm just going to pull it out in front as part of my greatest common factor. So I'm going to take this 5 halves, and it's going to go here. Okay, so that's gone. What's the greatest power of x squared minus 3 that I could extract? That's a common factor. I can only take out an x squared minus 3 cubed, agreed? Okay, so I take out x squared minus 3 cubed. What else? I can take out a 2x cubed minus 3x squared to what power? 3 halves. Okay, so we've got a right? And that's it. Now what am I left with if I do that stuff? Okay, so I've got here's my minus sign that's separating the two terms. What am I left with from the first term on top? I took out the 5 halves. I took out that, factored that out completely. And so I'm left with x squared minus 3, okay? And then I'm also left, it looks like, with this, right? With a 3 times two x squared minus 1. So that's everything that's left from that first term when I pull all this stuff out, right? Everybody good with that? Questions on that? Okay. Minus, and there's our big minus. What's left over here? Okay, what about the numbers? So I've got a 2 times a 4 is a 6, right? If I undistribute a 5 halves,
2 times 4 is 8.
Oh, sorry, it's 8. Yeah, sorry. just testing you. 2 times 4 is 8. So if I undistribute a 5 halves from an 8, what is that? Remember, undistributing or factoring out just means dividing by, right? So what am I going to be left with over there? I'm going to be left with 8 divided by 5 halves, which is the same thing as 8 times what the heck? If I undistribute, oh, I can't take out a, what am I doing? I can't take out a 5 halves. I can take out a 1 half. That was, okay, I gotta backtrack a little bit. I did something really dumb here. I did something real dumb. Here, let's, because you see what the problem is? I would end up with 16/5. 5 is not a common factor, right? We don't have any common factors. We've got a 5 and an 8. Those have nothing in common, but I want to get rid of that denominator. So I'm going to factor out instead, I'm just going to factor out a 1 half. I'm not going to factor out the 5, right? So factoring out a 1 half, if I'm dividing both sides by 1 half, what does that leave me with? It's going to leave me with a, I'm going to move this just a little bit, give myself a little more room here. So when I factor out a 1 half from 5 halves, I'm just left with a 5, aren't I? Right? If I undistribute a 1 half, well, 1 half times 5 would be 5 halves. So I'm left with a 5 there. What about on this side? 2 times 4 is 8. If I'm going to undistribute a 1 half from an 8, that's the same thing as dividing it if you want to look at it this way. It's the same thing as dividing by 1/2. What's 8 divided by 1/2? 16, yeah. So on this side, I'm gonna be left with 16, right? When I undistribute the 1/2, times, what's the other stuff? So this goes away completely, right?
16x.
I've got an X, good, okay, good, I got an X, thank you. Got an X, and then, how about this guy, how about that base? To the 1, good, right, because we're gonna do 5/2 minus 3/2. Cubed minus 3x, right? Okay, so let's just pause there for a second. I just kind of interrupted our train of thought when I made that mistake, but you see what we did then? Really, the hard part is, would you agree, this is the hardest part. It's not the calculus, right? I mean, you guys all pretty much told me what to do with the calculus without a hitch, right? I mean, this is just following the quotient rule with chain rule derivatives as a part of that. When you get down to here, though, this is the place where you want to try to, this is where you got to be careful. You know, we're going to pull the denominator out. We're going to find what are the greatest common factors. The thing that was weird that I really want to make a point of doing was, oops, when you have, a fraction in one of your two terms where it's not a common denominator, I would urge you to just pull that denominator out and make it part of the greatest common factor. So look at the advantage of that. When now in here, I don't have any fractions to work with when I'm expanding, you know, when I'm simplifying this whole thing, because that's kind of a mess, right? I mean, if I had a bunch of fractions to work with in there, that would greatly complicate my life. I don't want a complicated life. So let's finish this up. All right, so we got this stuff done. How about this in here? What can I do here?
Take out an X from the 2.
There's, well, if I could factor anything else out, that'd be great.
Could you take out an X from the 2x to the minus 3x? And you'd be left with x squared, or 2x squared.
I could do that. Yeah, oh, there you go. But then I end up with, so I could take an X out there. Then it's still, I'm still stuck. It's not gonna match any of these though, is it?
Well, would
Right.
it match x squared minus 3? Or there would just be 2?
I'd have a 2, if I take out an X, I'm gonna get a 2x squared minus 3.
Times 5 and 3, and take out
5 times 3 is 15. You did the same thing I did. Yep,
Could you scroll down a little bit?
sure.
Where did that 2x?
Which
Was
2x?
the 2x cubed minus 3x, where did the 2x down a little bit?
Wait, on.
It was
Left side, left turn or right turn?
16x.
Oh, was it pulled over?
Right.
Right, okay, yeah, I can just scroll down. So these became, I should have made that an 8x, shouldn't I? So these two combined became an 8x, 4x times 2x. And then when we undistributed the 1/2, right, I pulled that 1/2 out from it. Well, if I divide 1/2 away from 8x, I'm left with 16x. Okay, does that make sense? Okay, the part that generally makes it a little tough is that. You know, that's a weird step, to divide out that denominator. But trust me, it is a good step, it really helps. So long story short, we don't have time to finish this, but how would I finish this? This whole thing right here, I hate to say it, but this is I'm gonna expand this out, and it's just gonna be one big ugly polynomial factor. There's nothing you can do with this, that's what we're stuck with, right? So we'd end up with this stuff times some 4th degree horrible polynomial. Hopefully some terms cancel, but it's just ugly. I mean, that's, you know, this one's gonna be a bad factor. We could all do that, right? I'm just gonna, you know, 3 times 5 is 15, x squared minus 3 times 2x squared minus 1. I just distribute and add like terms. Over here, this is an easier one. I just distribute the 16x. And then I've just got a mess. Okay.
So easy, Evan.
Here's what's been.
Yes.